Hello, and welcome to the Sleepy Brain Science. I'm so glad you found your way here tonight. Wherever you are, curled beneath a blanket, stretched out in the quiet dark, or simply resting with your eyes closed, this space is yours. There is nothing urgent waiting for you here, no questions to answer, no problems to solve. Just a gentle voice and a very, very large universe for us to wander through together. Tonight, we are going somewhere that has no roads and no edges. We are drifting outward through the cosmos, past the familiar stars overhead, past the soft glow of our own galaxy, and out into the deep reaches of space, where some of the most ancient and remarkable galaxies quietly shine. These are not just collections of stars, they are chapters of a story that began long before our sun existed. And tonight, we are going to read a few of those pages, slowly, softly, without any rush at all. If these quiet journeys bring you some peace, I warmly invite you to like, subscribe, or leave a thought in the comments. It helps other sleepy minds find their way here, one gentle soul at a time. But for now, none of that matters. What matters is simply this. You are here, and you are allowed to rest. So let your jaw soften, let your hands go still, let your breathing find its own natural rhythm, slow and easy, in and out. And as the weight of the day begins to lift just a little, allow yourself to be carried. Let's begin. Every time you look at the night sky, you are doing something extraordinary without even trying. You are looking backward in time. The light from a distant star does not arrive the moment it is released. It travels, sometimes for millions or even billions of years, before it finally reaches your eyes. By the time that photon touches your retina, the star that sent it may have changed beyond recognition. Some may no longer exist at all. For the most distant galaxies, this idea stretches even further. The light arriving in our telescopes tonight began its journey when the universe was still young, when it was loud and restless and still figuring out what it would become. Distance and time in the cosmos are the same conversation. To look far away is to look long ago. Astronomers understand this deeply. When they point their instruments toward the edge of the observable universe, they are not just measuring space, they are reading history. And that history is still arriving. Night after night, ancient light crosses the cosmos and falls onto our mirrors and sensors, carrying information that has been traveling longer than Earth has existed. There is something quietly remarkable about that. The universe has been sending us messages for billions of years. We are only just now learning how to read them. Our sun is about 4.5 billion years old, which feels enormous, and by human standards, it truly is. But the universe is nearly 3 times older than that. In the time before our sun ignited, before our solar system formed, before the planet we stand on had even begun to take shape, there were already generations of stars living and dying across the cosmos. Those early stars did something essential. They were enormous and short-lived, burning through their fuel in just a few million years before collapsing and exploding in brilliant supernovae. Inside those explosions, heavier elements were forged: carbon, oxygen, iron, and dozens of others, and flung outward into space. Over time, those enriched clouds of gas drifted and mixed, gradually seeding the next generation of stars and the planets that formed around them.
Eventually, after several such cycles, the conditions were right for a star like our Sun and a world like ours. When we observe a galaxy from that earlier era, one whose light has been traveling for 10 or 11 billion years, we are seeing the universe before any of that had happened. We are seeing a place that has not yet learned to make the ingredients for rocky planets, for oceans, for the chemistry of life. It is a window into a cosmos that is still becoming. And yet, even in that young and incomplete universe, there is beauty. There are stars being born, gravity weaving structure from chaos, light pouring outward in every direction. There is a kind of observation in astronomy known as a deep field image. The idea is deceptively simple. You choose a patch of sky that appears to the naked eye to be completely empty, just darkness between the stars. Then you point a telescope at it and let it stare, not for minutes, not for hours, but for days or weeks, collecting photons one by one, patiently building up an image from the faintest whispers of light. What emerges from that long patience is breathtaking. A region of sky no larger than the width of your little fingernail held at arm's length. A space that looked like nothing at all turns out to be full of galaxies, thousands of them, spirals and ellipticals and clumped irregular shapes, each one a vast collection of billions of stars, each one at a different distance and a different stage of its life. Some appear sharp and detailed, others are barely a breath of color against the dark. These images carry a startling message. The universe is not sprinkled with galaxies the way a sky might be sprinkled with stars. It is saturated with them. Everywhere you look, if you look long and carefully enough, there are galaxies, beyond galaxies, receding toward a horizon we can almost but never quite reach. Once you truly absorb that, the night sky is never empty again. It becomes a depth, a thickness, a silence full of ancient light.
One of the quieter marvels of the universe is that gravity can bend light. Not dramatically, not in a way you would notice on a human scale, but on cosmic scales, the effect becomes profound. A sufficiently massive object, like a giant galaxy or a dense cluster of thousands of galaxies, curves the fabric of space around it. When light from a more distant source passes near that massive object, the light's path bends along the curve. It arrives at our telescopes from a slightly different direction than it originally set out from. The result can look like a painting. Background galaxies appear stretched into long, curved arcs, or multiplied into several copies of themselves, arranged in a ring. Astronomers call these gravitational lenses, and they are among the most useful tools in observational science. By measuring exactly how the background light is distorted, researchers can calculate the total mass of the lensing object in front, including mass that gives off no light at all. Gravitational lensing also acts as a natural magnifying glass. It can make otherwise unreachable galaxies bright enough to study in detail, revealing their colors, their structures, and the pace at which they are forming stars. Gravity becomes not just a force that holds things together, but a kind of cosmic instrument, bending the universe's own light into shapes we can read. There is something almost poetic about that, the universe showing us its secrets through its own weight. When a galaxy is very far away, its light has been traveling for so long that the expansion of space has stretched it. Imagine sending a sound wave across a room while the room itself is slowly growing larger. By the time the wave reaches the other side, it has been pulled apart, its pitch lowered, its wavelength extended.
Light behaves the same way in an expanding universe. Wavelengths are stretched toward the red end of the spectrum, and for the most distant galaxies, that stretching is so extreme that visible light arrives as infrared radiation, invisible to the naked eye. This is why some of the most ancient galaxies were invisible to us until infrared telescopes came into use. They were always there. They were always sending their light in our direction. We simply did not have the right eyes to receive it. Infrared observatories changed that, opening an entirely new layer of the cosmos to human curiosity, a layer populated by galaxies so remote and so old that they existed before the universe had formed many of the elements we consider ordinary. Color in astronomy is never just decoration, it is information. A galaxy glowing brilliantly in blue light is likely alive with young, hot stars, a place of active creation. A galaxy dominated by red and infrared light may be older, its bright young stars long faded, or it may be hidden behind curtains of dust that absorb shorter wavelengths and re-emit them at longer ones. Teasing apart the different explanations requires careful measurement across many colors, many filters, many nights, but the reward is a portrait of a galaxy's life, not just how it looks, but what it is doing and how old it is. In the young universe, galaxies were closer together. The cosmos was smaller, and the distances between things had not yet grown as large as they are today. This meant that encounters between galaxies were far more frequent than they are now. Not violent collisions in the way we imagine crashes. The stars inside galaxies are spread so far apart that two passing galaxies would lose almost no stars to direct impact. But the gravitational forces between them could be enormous, and the effects sweeping. A galaxy moving through another leaves long tidal tails behind it, streaks of stars and gas pulled outward by the difference in gravitational force from one side to the other. The gas inside both galaxies gets stirred and compressed. Where clouds of gas are pressed together, new stars ignite in sudden bursts. The shapes of both galaxies distort, twist, and over millions of years, sometimes merge entirely into a single, larger system with a new identity. Many of the grand elliptical galaxies we see today, smooth, rounded, seemingly calm, are thought to be the products of such ancient mergers. What looks like peace is the long aftermath of turbulence. The stars that orbit inside them do so in many directions at once, scrambled from the ordered rotation they once had when their home was a disc-shaped spiral. Galaxies carry their histories, even when their histories are no longer visible. The shape is a memory.
There was an era, roughly 10 billion years ago, when the universe was at its most productive. Galaxies everywhere were forming stars at rates that dwarf anything we see today. The cosmos had the right conditions: large reservoirs of cold gas, frequent galaxy interactions, and enough time for matter to have gathered into substantial structures, and it used those conditions fully. Astronomers sometimes call this period cosmic noon, the high point in the universe's star-forming career. During that era, a single galaxy might have been producing stars hundreds of times faster than the Milky Way does today. The skies of those early systems would have blazed with the light of hot young suns. Nebulae glowed across enormous regions. The interstellar medium was thick with the energy of formation. It was, in the truest sense, a time of building, of raw material being shaped into long-lived structures we see around us today. After cosmic noon, things gradually quieted. Gas supplies were consumed by all those new stars. Some gas was heated so intensely that it could no longer collapse into stellar nurseries. the rate of star formation across the whole universe began to fall, slowly but steadily over billions of years. Today, the universe makes stars at perhaps 1/10 the pace it once did. The age of furious creation has passed. What remains is its legacy. Billions of galaxies, each carrying the stars formed in that earlier abundance, aging gracefully in the long cosmic afternoon. Dust in space is nothing like the dust on a windowsill. It is made of tiny grains, smaller than a single bacterium, composed of carbon, silicate minerals, and ice. These grains are remarkably efficient at absorbing visible light. In the dense, star-forming regions of a distant galaxy, dust can wrap around the brightest areas and swallow their light almost entirely, leaving only a faint smudge where there should be a blazing beacon. For decades, this hid some of the most active galaxies in the universe from our view. Their visible light was trapped inside curtains of dust, and our telescopes could only see that faint smudge, if they could see anything at all. But dust does not destroy the energy it absorbs. It absorbs it, warms up, and then re-radiates that energy at longer wavelengths, in the infrared and millimeter ranges of the spectrum, which pass through dust more freely. When radio and infrared telescopes began mapping the sky, they revealed a hidden population of intensely star-forming galaxies that had been invisible to optical instruments. Some of these were producing stars at staggering rates, building their mass rapidly behind their dusty veils. Our census of the universe had to be rewritten. The cosmos was not only deeper and more populated than we thought, it was also more active. Dust had been concealing the universe's most ambitious builders. Seeing through it changed everything. Spiral galaxies feel like a symbol of cosmic elegance, their graceful arms winding outward from a bright center, their slow rotation carrying stars and gas in the same vast choreography for hundreds of millions of years. It might seem natural to assume that such orderly shapes would only emerge late in cosmic history, after the turbulence of the early universe had settled. Yet astronomers have found spirals at surprising distances in a universe that was still quite young. Forming a spiral requires a galaxy to settle its gas into a rotating disk rather than remaining as a chaotic, tumbling cloud. The gas needs to cool, collapse inward, and find a preferred plane of rotation. Spiral arms then emerge naturally from the rippling gravitational waves that travel through the disk, not a fixed structure, but a persistent wave, like a traffic jam that moves through traffic even as individual cars pass through it and continue on their way. Finding spirals early tells us that some galaxies found this calm, settled state faster than anyone expected. It also raises questions about how they stayed that way. The early universe was crowded and disruptive, interactions were frequent, and yet certain galaxies maintained their disks, preserved their rotation, and built the kind of organized structure we now take for granted in mature spirals like our own Milky Way. They found their balance somehow in the middle of chaos. That persistence is its own kind of quiet wonder.
At the center of most large galaxies sits a supermassive black hole, an object with a mass millions or billions of times that of our Sun, compressed into a region smaller than our solar system. For most of the time, these black holes are quiet. Their surroundings have little fresh material to feed on, and they sit in relative stillness at the heart of their galaxies, making themselves known mainly through their gravitational influence on nearby stars. But in the early universe, these central black holes were often still growing. Gas and dust fell toward them in enormous quantities, drawn in by gravity and heated to extraordinary temperatures as it swirled into a bright, dense disk. That disk could outshine the entire surrounding galaxy, every one of its billions of stars, by a factor of hundreds or even thousands. We see these blazing cores as quasars, and some of the brightest are visible across nearly the entire observable universe. A quasar's light is powered not by nuclear fusion, as stars are, but by gravity itself, by the conversion of infalling matter into radiation with an efficiency that stars cannot match. And because this energy is released from a very compact region, quasars can flicker noticeably over weeks or months, giving away their true size to patient observers. They are among the most extreme and energetic things the universe has ever produced. And yet, when we look at them, we are often looking at the early life of a galaxy that in its older years may have quieted into something much more like our own. Dwarf galaxies are the most common type of galaxy in the universe. They are small, containing anywhere from a few million to a few billion stars, compared to the hundreds of billions in a galaxy like the Milky Way. And their gravity is modest. Because of that modest gravity, the forces that shape them can leave clearer marks than they do in larger systems. A burst of supernova explosions can drive gas out of a dwarf galaxy entirely, temporarily halting star formation. A close encounter with a larger neighbor can warp its shape, compress its gas, or strip stars away in long tidal streams. These effects, which a massive galaxy might barely notice, can transform a dwarf galaxy entirely. That sensitivity makes them valuable. They respond more dramatically to the same processes, and so they show those processes more clearly. Some dwarf galaxies have spent their whole existence in relative isolation, and in that isolation, they have preserved a nearly unaltered record of their earliest stars. The chemical composition of those stars reflects the universe as it was when the galaxy formed, before heavy elements had spread widely through the cosmos. In that sense, the smallest galaxies can hold the cleanest archives. They are witnesses to a younger universe, undisturbed and quietly faithful to what they have always been.
When a small galaxy passes too close to a much larger one, the side of the smaller galaxy that faces the larger one is pulled more strongly than the far side. This difference in force, this tidal stretching, slowly pulls the small galaxy apart, drawing its stars into long, thin streams that loop around the larger galaxy in graceful arcs. These stellar streams can stretch for hundreds of thousands of light years. They curve through space like rivers made entirely of stars moving in slow procession along the orbital path their former galaxy once followed. Long after the original structure has been absorbed and dissolved, the stream remains, a ghostly echo of something that used to exist as its own world. Astronomers map these streams in deep images, tracing their paths across the sky with great care. The precise shape and trajectory of a stream carries information about the gravitational field it has been moving through, including the unseen distribution of dark matter that fills the halo of the larger galaxy. In this way, the remnants of destroyed dwarf galaxies become instruments of discovery. Even in dissolution, they tell us something true about the universe they once inhabited. We have traveled far tonight, across billions of light years and billions of years, through dusty curtains and gravitational lenses, past clumpy young galaxies and smooth ancient ellipticals, through the brilliant chaos of cosmic noon and the quiet rivers of dissolved stars. We have visited a universe that was still becoming and glimpsed some of the long, patient processes that eventually made it possible for a small planet to form, for oceans to gather on its surface, and for curious minds to look outward and ask, what is out there? What is out there, it turns out, is more than we ever imagined. More galaxies than there are grains of sand on every beach on Earth,
more stars than we could ever count, more light crossing the dark in every direction than we will ever have instruments sensitive enough to catch. The cosmos is not empty. It never was. It is luminous and ancient and astonishingly full. And tonight, we have wandered through just a small edge of it. You, right now, are made of atoms forged inside early stars that lived and died long before the sun existed. You are in a very literal and beautiful sense part of the same story as the galaxies we explored tonight. You are the universe looking back at itself, finding patterns, feeling wonder, and, right now, letting go of the day and drifting gently into rest. Let your body be heavy. Let your mind be still. The universe will continue its slow and luminous work while you sleep. There is nothing more you need to do tonight. You are safe, you are here, and you are allowed to rest completely. This has been Sleepy Brain Science. Thank you for spending this time with me. Sleep well.